webinar. It's my pleasure to introduce our speaker, Zhenhua Liu. Zhenhua is finishing up his PhD at Caltech, where he's working in the Rigorous Systems Research Group. He received several degrees before going to Caltech. His 2 bachelor's and 1 master's degree in measurement and control, computer science and technology, and economics from Tsinghua University and Peking University in China. His research interests include systems and network science with applications to renewable energy integration and energy management for big data and cloud computing. His PhD work has already been widely cited, and he's already received a number of awards even at this very early stage of his career. He's received multiple Best Paper awards at key conferences, and the Pick of the Month award by the IEEE Sustainable Computing Technical Committee. And he's also worked with several companies during his PhD. In particular, he's worked pretty closely with HP and Palo Alto and collaborated with them in implementing the industry's first net zero energy data center. And that accomplishment was recognized as a 2013 Computer World Honors Laureate. Most recently, he's received an award for Outstanding Students Abroad from the Chinese government. So Zhenhua is actually visiting us here as part of an interview for open faculty position in the dynamical systems and control area. We're very pleased to have him here. I actually didn't know Zhenhua before. I met him for the first time yesterday. We've seen him today. Either he dresses up like this all the time, or he's really taking the interview seriously. I've only seen him very dressed up, including the Skype interview we held with him last month. So today he's going to talk to us about his research and a bit about his vision for the future for sustainable IT and IT for sustainability. So please let's welcome Zhenhua.
Yeah, thank you, Lucy, for the fantastic schedule for the interview. I really enjoyed the yesterday's and today's morning session. It's really good to be here. And this area is kind of similar to my growing neighborhood, since I grew in a city which is also famous for its mountain. Some of you might know it's Mountain Tai in China. Yeah, so it's a very good place to visit. Yeah. So back to the research. So energy and sustainability have become one of the most critical issues facing our society, right? So although the abundant potential of renewable energy, such as wind and solar, provide us a real opportunity for sustainability, their intermittency and uncertainty present a daunting operating challenge. So for my own research, I try to design analytical models, deployable control algorithms, and real systems to enable efficient integration of renewable energy into complex network systems. So, okay. I'm sorry. Okay, good. So, I guess most of you are using Google services. But something you probably do not know is that these services cost Google more than 1 million servers. And here the emission, I mean the carbon dioxide emission of one server is equivalent to a car. And together with other IT companies, so IT produce as much emission as the airline industry. So imagine how many flights we have every day. Right? And for the energy usage, the worldwide data center as the building blocks for our cloud computing consumes about 2% of the world electricity consumption. What does that mean? That means if we consider all the data centers as a country, okay, we name it like United Data Centers, okay, then its electricity consumption on an annual basis is as large as United Kingdom does. So, and most important, this part is increasing very fast. It's much faster than the total electricity consumption does. So now it's only 2%. But for the future, 10 years ago, it will be 5%, and it will keep increasing. So this is a very important problem for us. And Greenpeace does a very good work to provide the statistics for this problem. They have 2 reports. One is how dirty is your data, one is how clean is your cloud. So these are very good reports. I suggest you to read if you have time in the future. So for my own research, during the past 5 to 10 years, I saw an emerging research dimension in networking and the system, which is energy and sustainability. So almost every traditional research area is now related to energy, to power, to sustainability, and even to our ecosystem, climate change. Right? This research can be divided into 2 areas. One is to make the IT system more sustainable, and the other is to use IT as a tool to improve the overall sustainability of our broader energy infrastructure. Okay. For my research, I did work on both parts. For the first one, I work on geographic load balancing and the implementation with HP Labs. For the second one, I work on particular demand response. 2 parts. One is for the user, how to manage its own load, and also for the utility company, how to design market demand response market programs. So here, one keyword here is Sigmetrics. That's my home conference. It's the best conference in modeling and performance evaluation. Yeah, this conference, the acceptance rate is very low. It's only 15%. And so I'm quite lucky to have several papers there. Let's start with the sustainable IT. Here, since the energy consumption is very huge, so it's not surprisingly to see there is a huge push from both industry and academia for this problem, right? From the air, from the cooling optimization to power distribution, and eventually, recently we have the data center in a container. Right? Some of you might be familiar with this one. And these are all very, very good improvements. As a result, the power usage effectiveness, which is defined as the power goes into the whole building, divided by the power used by IT system, which is used to do the real useful work, right? And we want this term to be as small as possible, and the lower bound is 1. All the engineering improvement make this to reduce from more than 3 just 10 years ago to the most state-of-art data center can have very, very good power efficiency. These are all very good news, but what's missing here? The missing part is that a lower PUE does not necessarily mean lower energy consumption, right? Because if we increase the power, the IT power, make the IT system less efficient, that can actually reduce your PUE. That's actually the trick some IT companies are playing now. They move the cooling power from the big blower and the mechanical chiller to the fan on the computer. And then they claim, this is IT power, right? Then you can reduce this one, right? But even lower energy consumption does not necessarily mean sustainability, because we need to see how much power is from renewable energy. This is particularly important now, because I see more and more data centers, they are built as a location with very cheap electricity price, but very dirty. Right. So for my research, I focus on improved sustainability. So this is my first research dream, to make data centers sustainable. Yeah. And so the goal is to power data center with renewable energy. So for data center, we have the IT demand, which we need to meet. Yeah. And we also have other overhead, like cooling and maybe lighting, a lot of things. And for the power side, we have local renewable generation, right? Such like a new Apple data center, they have a 20 megawatt local PV generation, which is a huge. They use several acres of land for the PV panels. It's huge. And we can also use the the power from the electricity grid, which you probably have time-varying electricity price. Right? So both parts, the demand supply, they're dynamic and uncertain, that they do not match each other. Right? This is a challenge. So this is an example of data center power usage profile. And the red curve is PV generation, and the blue bar is IT power, and with IT capacity constraint. And the brown bar is the cooling power. And the goal is to make it look like this through workload management. So what makes this possible is workload is flexible. This flexibility is in two folds. The first one is a flexibility in time. Right? So if we take a closer look, there are actually two classes of workload in data center. One is critical workload or interactive workload, such as Google search. Right? We need to meet the demand immediately. Usually the deadline is millisecond or 1 second. Right? So for this kind of workload, we do not move. But for the other, a lot of batch jobs, right? Like scientific computing, like the image processing, now we have a lot of big data applications there. For this kind of workload, we have much larger flexibility. For example, when I work at HP, they have one image processing job for Disney. And that job takes the whole data center for several weeks to finish. So for this kind of workload, you can have quite a large flexibility to decide at what time to serve the workload, as long as you finish before the deadline. Right? So we can shape the delay tolerant workload to do the demand shaping. Okay, I have the workload. I have the work along this line. And for the spatial one, it's kind of a unique flexibility in data center system or in the cloud. Right? So here, I call it geographic load balancing. I will talk in detail in the following slides. So here we need to design, since it's a large distributed system, we need to design distributed control and also the online control to deal with the uncertainties there. Right. Okay, for geographic load balancing, what's that? So let's take Google as an example. It has around 20 data centers in United States. Although I show United States, this one can be global. And here, they have data centers at different locations, probably to minimize network delay, to increase reliability, but this makes the routing challenging. Right? To see this, here in this system, the proxy, the request will first go to the proxy, and the proxy will decide where to send the traffic to. Right? For example, for here, we just go to the data center at California. For this one, probably just go to the Atlanta. But for the request here, we probably want to split between different data centers. Right? So we call it energy-aware routing because it makes trade-off between load balancing, network latency, as well as the energy conditions. So all of these are time varying and location dependent. So after you make the routing decision, the data center will know its incoming load, right? And then, given this incoming load, it will decide number of active servers for each time slot. So we call this dynamic capacity provisioning. Yeah. So, okay, I have a demo here to better illustrate the idea here. I call it follow the renewable routing. Okay, here is a legend. The left-hand side is the demand, and we have the power, the IT power and the cooling power, the yellow part and the blue part. On the right-hand side is a generation, it's a supply. We can have the grid, we can use the electricity from the power grid, which is red, which we want to minimize. And we also have the wind and solar renewable generation. So there is not very clear, but there is actually a circle outside that is the total capacity of the data center. The larger means we have more active server inside the data center. So now we can say as time goes by, so each data center do the dynamic capacity provisioning, and all the proxies are making their decision according to the renewable generation. So here is that one thing is that we do not move traffic between the two coasts because the delay is too large. But we do care about the middle part. It matters a lot. Okay. Okay, so for this one, our goal is to design deployable and distributed control with theoretical guarantees for this follow the renewable routing. Yeah. The deployable and the theoretical, these are two words I really care a lot. Since if it's not deployable, it's really hard to validate your value in real system, especially to industrial people. Right? For theoretical guarantee, it's also very important since if we do not have the theoretical guarantee, if everything just goes well, it's okay. When something goes down, you have no idea what's happening there. Right? So these two are the key for my research to be appreciated both in academia and the industry. And also the distributed one is particular for geographic load balancing, since it's a large system. And for ECMI, it has thousands of data centers in United States to serve the request. So it's a large distributed system. Okay, the way I will go from analytical modeling to deployable control algorithm design, and then to use it to evaluate its impact using real traces, and eventually go to industry to implement the real system to have the real impact. One thing I want to stress here, okay, this is my research philosophy, just rigor plus relevance. Maybe you will have a better feeling at the end of the talk. Okay, for model part, okay, this is system. For the proxy or mapping node, we have the workload. We discretize the workload to each hour. Okay, since for the renewable generation, we do not need to respond too fast, such like a TCP congestion control data. We just need to respond in 1 hour is already enough. It's already good enough. Of course, if you can do a finer granularity, it's even better. But here, 1 hour is enough. And then we get the demand for current time slot, which is, okay, from now in the following 10 minutes, you will see notations here, which I try to minimize, but still, sometimes it's necessary. But I promise it's just 10 minutes. After that, there are no notation. Yeah. Okay, the mean request rate for the current time slot is denoted by LJ. It's for each proxy. Okay, we also have the online algorithm design to deal with the uncertainty in the future. But in this talk, I focus on the distributed design. Okay, when we have the total arrival rate for each proxy, it need to decide the traffic from the proxy G to data center I, or lambda ij. Right? This is a routing decision. We call it energy aware routing or year. And for data center, okay, it has a total number of servers, capital MI. The electricity price, PI, the power usage effectiveness to include all the overhead, EI, and also the local renewable generation if you have any, that is small RI, and also the arrival rate, lambda I, which is a summation of all the lambda ij over G, over all the proxies. Right? Given this, the data center need to decide the number of active servers for current time slot, which is a small mi. Right? This is a model. Okay, then the system, the cost is two parts. One is the energy cost, one is the delay cost, because we care these two together. And usually in cloud computing, the owner will value this together. It's not an explicit constant. Usually it's an internal trade-off between these two. That's why we have this combination form. It's also more challenging. And for energy cost, for data center I, it's a function of your number of active servers, and it's also related to the electricity price, renewable generation, and your power efficiency. Okay. For delay cost, we have both network delay, which is Fi. Okay. This is a queuing delay in the data center, which is a function of number of active servers and the load. We also have the network delay. Then we transform this delay using a loss revenue function into cost in dollars as the average result. Okay. One example for power costs is in this form, right? So this is IT power we transform user power effectiveness and get the total power minus the renewable generation and then times the electricity price. This is just one particular example. And for this one, we can have, this is the queuing delay for MGR1 processing sharing queue in data center. And this is just a delay. And we use linear loss revenue function to transform this one. Okay, so these are just two examples to help you to understand what's going on there. But in the algorithm design, we focus on a general form of the problem. So here, what we can minimize, one is the MI, which is a dynamic capacity provision, number of active servers for each data center. Also, lambda ij, right, is the energy aware routing, the traffic from proxy J to data center I. We also have a lot of constraints. For example, the first one is that you need to finish the total amount of load for each proxy. Second one is just non-active. The third one is the number of active servers is smaller than the total number of servers in the data center. And this one, we ignore the integer constraint because in data center, number of servers is huge. It's usually thousands of servers. So relax that does not bring much inefficiency. And last one is very challenging. That is to ensure the data center is stable. The arrival load is smaller than the service rate. Otherwise, you will feel the infinite delay within this time slot, say several minutes, which is not acceptable for data center. Right? But this one, this lambda is the aggregated action from all the proxies, right? So that's a challenge for distributed algorithm design, which we will see in the following slide. Okay, one observation is that under mild assumption, this is a convex optimization problem, and so we can solve it using centralized algorithm. But the challenge here is how to make it distributed. Okay, now we come to the algorithm design. So any questions so far? Okay, good. Okay, before my work, there are actually some other work on the distributed algorithm design, and they also claim to work closely with industry to deploy the system. But none of them give guaranteed optimality for this system. Usually it's a heuristic algorithm. Okay. So for my research, the first key idea is a separation between the routing decision and the capacity provisioning decision for data center. Right. Here, the basic structure looks like this. For data center, for each data center, given the incoming load, it can solve a local optimization to decide the number of active servers, right? So this one is okay. For some form, we can even write a closed form for data center. This one can be solved in a distributed way, that's okay. And once it decides this parameter will go to the routing decision. And each proxy needs to make the routing decision independently, which is very challenging. But assume we can do this one. Okay, if we can do this one, then this process will go on and until we reach the optimal solution. Right? And we can prove there is no efficiency loss from this separation. So this is good. So the remaining challenge is really how to make the routing in a distributed way. But still, we need the optimality guarantee in the sense of it will convert to the optimal solution. Okay. So see the challenge here that for one particular proxy J, this is its feasible set. 3 constraints. The first 2 are okay. Right? The first one is just you need to send all your traffic out. The second one is just non-active. So these 2 are okay. It's just your decision. But the third one is challenging. Right? It means your traffic plus the traffic of all other people should still within the service capacity of the data center. Right. This is a challenge. So the traditional way to deal with this one is that from the current state, we calculate the gradient projection direction. To calculate the gradient direction, and then if it goes out of the feasible set, we go back to the projection. But here, we do not know how to do that. The calculation of the gradient direction is easy. But when you go back, you have no idea. The reason is that the first one, we want the objective to decrease for each time slot. Okay, here, our goal is that the objective will keep decrease, no oscillation. Will keep, but the objective is not smooth enough, or in particular, it does not satisfy the Lipschitz condition. The reason is a queuing system, right? If the arrival rate approaches the service rate, the delay will go to infinity. Right? That's the assumption required in traditional distributed algorithm design, but we do not have it here. Mm-hmm.
There's one quick question here. So you talk about timing granularity, it's like hourly basis, right? The traffic is basically the timing granularity of the traffic is much finer, right?
Yes.
So even consider that, you still think this one's not
Okay, it's a very good question. So it's kind of two-level problem. The first one is that we have the diagonal pattern, right? For that one, it's quite stable. But can you do something with that, right? If you can achieve that with a slow time scale, then the next step is that can you do it faster so that we can satisfy the requirement for the fast fluctuate workload. But here we first focus on the first one, but later I will talk a little bit about how to do that one. The second one is that we need that to be distributed, but the constraints are coupled. Right. Okay, so the solution is that we make conservative move. How to do that? Is that from the, okay, we first get the initial point. We assume we have an initial feasible point. No matter it's optimal or not, it's okay. Just a feasible point. That's usually attainable because the system will ensure it goes to a feasible set. And from the feasible set, we define a constrained feasible set. It's actually a level set. It contains all the points with the objective value lower than the initial value. That's why it contains all the optimal solution. And if we keep decrease, it will always stay in this feasible set, in this blue one. And then from the current point, we still calculate the gradient and project back to this one instead of the original one. By doing this, because within this blue one, the objective function is Lipschitz. Then we can get this one to make sure it will keep decrease. And when it decreases, it stays in the feasible set, and then it keep decrease, and this goes on. And so this part is okay. The second one is we want to do it in distributed way. This one, my idea is that we scale the projection, not directly go to the boundary, but scale it by the number of proxies. And by doing this, we can prove, even though every proxy is doing the decision independently, as a whole, they still stay within this set. And the people might worry it will go too slow since we make conservative move. But here, we scale by the number of proxies. So if one data center is particularly popular, so all the proxies will send traffic there. So aggregate together is still can recover the speed from the centralized control. Okay, so this is the general idea. Any question?
Did that really solve the distributed nature, because every proxy still needs to know what every other proxy?
You just need to know the total number. You do not need to know the decision of other.
Okay.
When you make the decision, you pretend there is no other people, just you. Okay.
So you're scaling it down in such a way that if even everybody made the decision along that gradient, that we still live within that boundary. And so when everybody gets large, that means you're moving at a very, you're moving incrementally small. So do you get a slow down due to the conservative?
No, as I just described, right? If you have a large number of users, then each one just make 1 over the number of server, but the aggregate them together is still the same. Okay. Then we can prove within this structure. So if the step size is small enough, then every limiting point is optimal. By small enough, we have a complicated the notation expression for this one. But two idea here is one is a proportional to one of the number of proxies. A second one is that when we have high load at the data center, we will make small move. That makes sense, right? So when the data center is already at a high load, kind of congested, you need to be careful so you do not go out. But during night, if it's okay, then you can move faster. Okay. Okay, this is a picture I really like. I want to share with you. Is that some of you might already see this one. Okay, so this is this is our human knowledge, and as a student, we start from elementary school to gain some knowledge, and then from high school and from college. Here, one thing is that for college, we begin to have some major, which is might not be a good thing or bad. I'm not sure, but that's a reality. Right? So, and then you get your master, you go along that way. And eventually you get your PhD here, right? And okay, and we zoom in, that's something you make. Okay, if this is true, okay, the past slice is what I made here. That's I think that's the advance in kind of our knowledge of how to deal with the unsmoothness in objective, but still we want to have the distributed algorithm design. So in the future, if you want to design a distributed system, but your objective is non-Lipschitz, you no longer need to worry about that condition. Yeah. So we are preparing a paper for transaction on automatic control for this theory part. And even, right, so okay, go back to your contribution, right? Even though I feel it's a big contribution for myself, but for the total, it's still kind of negligible, right? So that's why we need to keep pushing to have more and more contribution along this line. One particular interest one is that I'm not sure whether you know Professor John Doyle at Caltech, but one particular thing I'm collaborating with his student is on localized control. Yeah, which is a very good topic. And if you're interested, we can discuss during one-to-one, or tomorrow we have a coffee hour and a lunch. You're all very, very welcome to come. Okay, then as I promised, so this is the end of the notation part. Now let's go with the normal human language about the slice. Okay. Besides the convergence, we also have other practical properties. One is, okay, the convergence rate, right? This is the optimal solution as you just varied. Okay, our algorithm back 3 years ago is already converged okay. Recently, we come up with a new algorithm. It's accepted by transactional networking, and this one is converged very fast. Actually, we have the idea of the algorithm 3 years ago when we submit a paper to Sigmatrix. But it takes 2 years to come up with a proof that it actually can converge. Yeah. And another is that people might worry that the routing decision is too complicated or too fragmented. But actually, we can prove in a graph, if we consider every data center and every proxy as a node in the graph, and when there is a traffic sending from the proxy to data center, there is an edge, then we can prove there is a simple optimal solution that there is no circle in this graph. So what does that mean? If you have 20 data centers and 1,000 proxies, on average, one proxy only sends to one data center. But you still have some split for some proxy. And the proof is constructed. Okay, the last one is that the optimal solution in general is not unique, but the per server arrival rate is unique across all the optimal solution, which is an important factor for data center operator. Right? Okay, within this, I began to evaluate its impact. This impact is twofold. One is for data center operator in terms of energy cost in dollars. One is to the society in terms of the emission. Right? Okay, the setup is that we have 10 data center locations, and we use the industrial electricity price for each location, and it varies for different location. And for workload, we have one proxy for each state, and we use the workload of Hotmail, and we scale the workload by the number of people with internet access in that state. Okay, and then the network latency is proportional to the geographical distance. Okay, this is the model. So the first one is that from the data center operator's perspective, so how much cost can we save over heuristic approach? But heuristic is still quite strong. It's kind of the current practice in industry. Is that it's even better than the current in industry, but I will talk that later. It's local, we call it local. What does local do is that it still do the optimal dynamic capacity provisioning for data centers, but the routing is the nearest routing. Okay. Then compare with this, for the system host cost for the 2 days, compare with the local, we can save up to 20%. It's already quite significant for data center operator. And the reason behind this is that we save significant energy costs, but we still increase, but we only increase the average delay a little bit. As you just see in the demo, right? We do not send traffic along the two coasts. But if we see the energy usage, it actually can increase. The reason behind this is when we send the traffic to a further data center to utilize the cheaper electricity or renewable energy there, we need to turn on more server to compensate the network delay. Okay, then we need to consider how can geographic load balancing to be also environmental friendly. Here the answer is to use it for follow the renewable routing. Okay, there are two approaches. Okay, sorry, it's again, but you can just, it's not very important here. Two approaches, just consider this objective, right? One approach is that you can do dynamic pricing, that you can affect the cost of the data center. Another is that when data center have local renewable generation, it can also affect its local costs. So these are two ways to provide incentives for data center operator to do the following renewable routing. Okay. This is a simulation for renewable supply. Okay, we use real traces for East Coast and West Coast data center location and aggregate them. Okay, we can see there is a clear time difference there. And if we just do static pricing, as I described before, then the number of active servers for East Coast and West Coast look like this. Also, we have the diagonal pattern, the time difference. And if we can have dynamic pricing, in particular in this simple form, it's kind of a carbon tax. Okay, the price is a function of the dirty energy and the clean energy, and then we average them using the ratio of clean energy. If we can do this, we can see this one will follow the renewable generation. Yeah. By doing the follow the renewable routing. Another way is that to have local renewables. Here, what we need to care about is the renewable capacity required to reduce the power electricity consumption from the electricity grid by a significant amount, say 85%. So here is a wind and the solar capacity. Here, it equals to 1 means the average generation equals to the average demand. Okay. So if we only do local, it's very high. But if we can do geographic load balancing, even under low, not very expensive electricity price, we can do significantly better. And if we can have high energy price, such like India, right? India have very high electricity price, also maybe Palo Alto, right? Something like that. Then we can further reduce the capacity required. Okay. Okay, so for this one, the message here is that we can reduce the energy cost, which is good for the data center operator. We design the distributed algorithms with guarantee to convert to optimal solution. And we also design online algorithms, which I do not have time to show in this talk, but if you are interested, we can talk offline. It's actually a kind of attention to your work on receding horizon control. And and another is that it's also good for the society in the sense of it can ease the renewable integration. And here, by doing the following renewable routing. Okay, here is now I will go to the system part. And here, the whole system. For the routing part, it's challenge in theory to come up with the routing algorithm. But in practice, the system is already there. There are a lot of known techniques to implement that. So in particular, Google has a global workload management can apply this very easily. For data center part, the dynamic capacity provisioning is not hard in theory, but in practice, data centers do not do dynamic capacity provision. What they do is just leave all the servers on all the time. That's why in last year, New York Times have a report on data center utilization. The average utilization of data center now is only roughly 10%. So it's a huge waste there. That's why here we need to have some system can actually do dynamic capacity provision. That's why after my second year, after I have one Sigmatric paper, one best paper award, I go to my advisor. Since you need something already there, right, to negotiate with your advisor for collaboration in real system. Actually, they are all very supportive. That's why I spent the past 3 years to work with HP on this implementation. So this one, for data center, it's actually have 3 components. It's a IT cooling. You can have a cooling microgrid, and also the power supply. So all the information are collected by our capacity and workload planner to get the schedule, to minimize the environmental impact, to reduce the electricity cost, but still meeting the service level agreement for workloads. Okay. So the system architecture looks like this. We predict the renewable generation and workload, and we take in all the other parameters in, and then we generate the workload schedule and the resource provisioning plan for our runtime workload manager. So the planner here is that we need an analytical model of the system, then we do the control. The control can be local, just for one data center, and it also can be global, just as a dynamic capacity provisioning for geographic load balancing. Okay. And for the runtime workload manager, this is quite time-consuming, yeah, as you can imagine, right? So we do co-location of critical workload and delay-tolerant workload to improve the utilization of the server, but still keep the performance of the critical workload very comparable to just do it separate. And we do the live migration when needed. And we also do the cooling optimization. We have a lot of cooling expert at HP Lab in my group. And we also do the reactive control. Since this one uses a prediction, right? When the prediction is not accurate, you might want to do a feedback control for the system. Okay.
Question?
Mm-hmm.
Do you use a depreciated model, cost model for your PV? So you've got on-site PV,
Mm-hmm.
but it has some cost. And so do you put a cost
No.
against that?
In this one, no. As I just did, we assume once you install, the operation cost of PV is negligible. But later, I actually have one paper on the life cycle analysis of sustainable data center. There, we need to consider the capital cost of the PV generation. there,
Sure.
of course,
And do you consider the possibility of selling back to the grid?
yes, yes.
In the balance?
Mhm. Okay, this is a demo for what's going on in that data center. Okay, these are three parts. This is a power. We have renewable PV generation and the electricity grid. We have a switch between these two. And this PV is actually on top of the building at the HP data center. And the IT part, I just show 3 physical servers, but we have many more. So for this one, when it's green, it means it's active. Otherwise, it's in sleep mode. And all the brown boxes are virtual machine on the physical server. And here for the cooling supply, we can have outside air cooling when the temperature is low, and we can also use the traditional chiller cooling. Okay. The lower part just the statistics of the system. You can ignore it for now. Okay. Then, as time goes by, now it's just night, right? So we do not have renewable generation. We only use one server, and we use outside air cooling. And later, now it comes the day, we have more renewable generation. And then we turn on all the servers to serve the load, and we use the mechanical chiller cooling because the outside air temperature is high. Yeah, and later it goes back to night. Okay, that's the time of the day and the outside air temperature. Okay. Yeah, this shows what's going on there. And last year, in June, HP released the industry first net zero energy data center, and it's got the Computer World laureate. And more importantly, this work is integrated into HP product called EaglePod data center, which is used by major IT companies such like Facebook and Apple, and also national labs such like NREL here. And I just show a picture that this data center used by eBay. So this is what I'm most proud of for my research, to produce some practical value. Okay, so we go through the whole process for this project. And then we still, so make IT more sustainable is only my first research dream. The second one is to use IT as a tool to improve the overall sustainability of our society. Not only power system, actually it's a society. So 2 parts here. I will talk with this one. So nowadays we have more and more renewable generation, and from the sustainability consideration. Right? For power grid, it's kind of 3 stage. First, they care about the cost. Then people worry about the reliability. Then we care about the reliability. People care about the sustainability. Now we care about sustainability. People begin to care about the cost. Right? It's kind of circle. And this shows the worldwide renewable energy capacity during the past 10 years. And it increased a lot. And among all the sources, wind and solar increased fastest. This brings a significant challenge for power grid operator, since there is a constraint that the supply should match demand in power system, right? Traditionally, what we do is that we predict the demand, since it's kind of the passive demand. And then we control the supply, since we can control the supply, to make the generation to follow demand. But now with PV and wind, the supply side is less controllable, and we have high uncertainty there. Right? Although we can use energy storage to solve the problem, but it's very expensive. That's why people begin to consider if we can also make the demand side responsive, to make the demand to follow the supply, at least to some extent, through demand response. Therefore, we need a huge increase in demand response. Right? People consider EV, electric vehicle, air conditioning, and even pool pumps as a candidate for demand response. But here in this talk, I will say that data centers are a promising alternative to demand response. The reason is that it's very large load, right? Each is very large, and it's highly automated. All the control knobs are already there. As I just showed in the demo, you can already control everything. But for the air conditioning here, probably you need to install actual things to control the system. And it's increasing very fast. And we have significant flexibilities, like not only workload management, but also cooling and lighting, as shown by Lawrence Berkeley Research Lab. They are working on that. And also, by default, data center should have on-site backup generator and energy storage. So this can further add to the flexibility of data center. So with all the flexibilities, what we can do? So in my recent work, actually, we just got the notification yesterday about this one. Is that, okay, this is a message. So the worldwide data center for demand response is a multi-10 billion market. It's a huge market. So how I get this number, right? We use the Southern California distribution power network. And here, because they are now deploying a very large PV panel in the power network. So the impact of this one, since PV it will fluctuate a lot, right? It will have a bad impact on the voltage of all the buses in the system. Right? When the voltage goes out of the region, the acceptable region, then there will be a voltage violation. Then we want to use either data centers or energy storage to reduce the voltage violation when we have a large renewable generation. Okay. So our results show a 20 megawatt data center with only 20% of flexibility can provide the same voltage violation rate as if we have a 3 megawatt energy storage. And this energy storage is very good storage. It is optimal located in the in the network, and it's also the charging and the discharging rate is very high. So from this number, we calculate this one. So the potential is huge, but the reality is that we have a lot of programs, but the data center rarely participate. The reason behind this is we have a challenge here. One challenge is engineering challenge, how to design algorithms under uncertainty, right, for data center operator. Since there will be huge risk associated with this program. Another is a market design problem for utility company. If you do not design the market, the charging scheme in the good way, then even though the data center participate, you still do not have the desired outcome. Right? So I'm working along these two projects, and what I want to stress here is that it's actually a challenge to combine both engineering and economics. So assume one day if we completely solve the engineering problem, we have a perfect controller for local data center. Is the problem solved? No. Because your demand response might not be good for the society. Right? Assume one day we completely solve the market problem, we have perfect market design. But if the local customer, if they do not participate, the market is just useless. Right? So this is a kind of interdisciplinary research that requires a lot of input and a lot of effort, I think, in the following 5 to 10 years to make the potential I just showed in the previous slides a real reality. So I guess for my own more background, I have background in both sides, so that can help me to push this research forward. Okay, so the hope is that the circle, as I showed before in my geographic load balancing research, can still be applied here. I'm currently also working with utility companies and IT companies on this project. So okay, this is, if you can only remember one sentence for my research style, this is the one. So I hope it's easy to memorize. Yeah. And okay, for my research, I start with the data center, together with HP, and to use it for the cloud to do the geographic load balancing. Here, I work with Google and Akamai there. And then recently, I work on the data center demand response for the smart grid. And I work together with utility company and Lawrenceburg National Lab on this part. And actually, the cloud, the geographic load balancing is a very good opportunity for demand response in a sense of we can move bits, not watts, which is very good. Since watts move the electricity power, it's not easy. Sometimes it's even not allowed. Since the U.S. power system network is separated, divided into several regions. So when you go across a bound, it's not easy. But for the cloud, we can go anywhere, right? That's why we want to have a cloud. It's actually commercialized by a startup called Cloud Energetics. And okay, we advise that company, but we are not part of the company. Okay, and also the cloud can be a very good cloud platform for smart grid, from the information gathering and the decision and the implementation. Also inside the data center, I also work on the platform for big data, both the networking algorithm and the big data analytics. Here I work together with Cloud Azure and Amp Lab at Berkeley. Some of you might know the Amp Lab. And this one can also be used for smart grid. For example, we need to do machine learning or data mining to get the understanding of customer behavior, which is useful for smart grid. So this part and this part are my most recent research effort. And so, okay, this region is to make IT more sustainable, and this region is to use IT for sustainability. This is my dual view of IT and sustainability. So along all the line, it requires control, either distributed control, online control, at different levels of the system at different time scale. And that's why I'm particularly interested in this position here. So yeah, that's the end of my technical part, and finally I want to acknowledge my collaborators at Caltech, my advisor, Professor Adam Willman and Professor Stephen Lowe, and also a lot of researchers at HP Lab and other industrial collaborators. Yeah, thank you.
I had a couple technical to start out. You were careful to pick an objective that was convex and you got a convex problem, and then later you're talking about multiple optimal points. Something didn't connect between those two. You have a convex problem, it's going to have unique solutions. So
no. Only strictly convex optimization can have a unique solution. General convex optimization can have multiple solutions. Right.
I guess I could have a continuum of some sort.
Right.
okay, fine.
Instead of vertex, you
Okay,
could
so
have an
one
edge
or
something.
infinity. Okay, cool. So you get, and then the same question was, you relaxed your, technical question, you relaxed the constraint of integer, which was just another smart thing to do because integer programming is really difficult. So when you're done, you get you get the MIs that are 1.3, 2.7. That's obviously you can't implement that. You either got to turn on one server or two. You can't turn on 1.3. So do you have any results? I mean, there are a lot of servers here. Do you have any results to how much optimality you lose when you?
Okay.
First of all, how do you handle that? Just round?
Okay. Yeah, what we do is round. And the thing is that, as I just said, in data center, it's a large number of
It
servers.
makes a difference.
Sorry?
I said ceiling instead of round.
So yeah, 1.3.
Round up.
Turn on, just round up.
Usually the thing is not 1.3, it's 1,000.
No, I understand.
0.3, right? Then you round it.
Units you are.
Yeah.
My units are thousands of servers.
Yeah, that's why in data center. But I agree with that.
Optimization is smaller.
Yeah, the integer the integer problem is actually a very interesting one. For example, in communication network, for example, for people are also considering the energy problem in routers, right? The communication network. In routers, now what we do is that, okay, assume we have a link from here to Denver. What we actually do is that we have maybe 10 physical links to connect these two. But for the user, you just seem like it's one link for you. For this 10, you can decide how many you want to turn on. 0, since the number is small, the integer is actually a big problem. Yeah. I saw some research along that line. The integer programming itself is very interesting direction. But here, just in my problem is that we do not have that constraint.
And then the second question is more general. And just curious, out of all the power that goes into data centers worldwide, whatever that number might be, how does that split up between power used on the computers and power used on the cooling? And I agree you can fudge those two because...
Oh, we have meters there. To meter the power goes into different components. For example, IT part and the cooling part, they might not in the same building. The mechanical chiller might have its own building.
Regardless, what's the breakdown? Is it 80% of it's really used for cooling and 20% actually powers electronics, or is it 50-50? What is the
Okay, that's a good question. That's what I showed for the power usage effectiveness. 10 years ago, is 3, which means is 1/3 goes to IT, 2/3 goes to cooling. Now it's much better, but the best estimation, as I saw, so different people have different estimation, but the average is half-half.
But part of that half includes turning a fan on the back of the computer.
Oh, sure.
Thank you.
You talked a little bit about how there's a lot of uncertainty in this problem, and I think that, the power system that I'm more familiar with is in Pennsylvania, the PJM system in Pennsylvania, New Jersey, and Maryland, which is very deregulated, which means that the generation is not, tied to whatever the other.
Yeah, there is the trend for
The point is
deregulation.
that It seems as though because of that complexity, it would be really hard to kind of say, the price is not linearly tied to kind of what generation technology is
No.
used.
Yeah.
So how could a system like this work in that kind of crazy network?
You mean which part of the world?
Well, because one of the variables that you have is price. We didn't talk a lot about how.
Oh,
you
okay,
said the
okay,
price
I
is
see.
different, But if the price changes, how does that?
That's okay, we solve for each hour, right? If it's just change hour by hour, it's okay. The challenge part I see is that if you it's actually in the demand response part. If you combine the localization of data center and the power network, in particular the optimal power flow problem, if you combine these two together, you might have some challenge there. So first, the optimal power flow is a foundational problem for power system operation. You need to decide for each bus how much you want to generate and how much you want to use. So that problem in general is not convex. So it's not easy to solve by itself. So even we can solve it in an efficient way, still the integration of the power system and the customer is not straightforward. Yeah.
So it just doesn't.
There is not, currently the practice is that the utility company will decide the price, right? Give you the price. But in the future, if you combine them together, there might be some other variable emerges as the price scheme.
And just a quick follow-on, kind of just a comment. I think that it would be really interesting to move into kind of looking at some of the environmental aspects of this problem, because again, when you're talking about sustainability, you think about cooling, if it's half and half, things like climate change or changing weather patterns are going to change the amount of cooling that
Sure.
we need.
Yeah.
And I think that if some of those variables are in the ancillary parts of the system, it may be interesting to bring some of that.
Sure, of course. And also there is a very good report by National Academy of Science on how to use IT to improve the accessibility. It's mainly all proposals, but it's very interesting report about the opportunities there. Of course, that's something we should care.
So I'm still thinking about the cost issues.
Mhm.
Right, so if I'm Google and I can place a data center, which is vastly different than HP's
Mhm.
portable unit,
Mm.
near hydropower,
Yes.
okay, it's one. So I don't have to necessarily build any renewables on site.
Mhm.
And you might have to differentiate
Mhm.
in the price from the utility renewables versus
Sure.
non-renewables in the model.
Mhm.
If I'm, however, putting a large data center, not the smaller
Mhm.
semi version, but
Mm.
a large data center, and I need to build my own
Sure.
renewable.
That's something Apple and Google
Exactly.
does. They all
And
have
so-
local renewable.
So how can you possibly ignore the sunk cost of
Okay.
putting in the renewables and not, at least appreciate the
Hmm.
sunk cost and provide a pricing of that renewable
Yeah.
to balance against utilities?
Yeah, that's a great question. So I don't ignore this factor. Actually, I worked for 1 summer for that project. So the total cost of ownership of the data center, not only the capital cost of the renewable generation, also the management cost and the human cost for all also the software, the IP cost for the software, right? All of these factors. So what I show here is just when you already have the renewable energy installed there, how should you do in the operation? Right. Another question built upon this is that if you want to build a data center, how should you plan for IT, for cooling, for power, right? So the other paper we actually have is to solve that problem. How do you still keep the operation in mind, but the goal there to optimally decide the capacity for each one. There is a cost for PV panel and also the installation and also the incentive from the government actually matters a lot.
Sure.
Yeah, I completely agree with you. That's a big factor that all usually ignored by researcher, but I do work for some time on that problem. And the even extension of that is that I'm not sure whether you know Dr. Chandrakant Patel is a former HP lab director. He come up with they call it the exergy as a currency for sustainability. So not only consider the cost, but consider the energy we completely lost from the law of the thermodynamic law. Yeah, so that's kind of the even high level thinking about the sustainability there, not only the life cycle, but also in the energy.
And are there, either in your thinking or in stuff that you've seen,
Mhm.
any considerations to storage associated with this?
Yes, our model can have storage. We actually study the impact of storage. Yeah. It's helpful, but it's more expensive.
Sure. Just a comment.
Hmm.
Your storage costs can be very different in terms of what batteries are probably the most expensive.
Mhm.
Pumped hydro is.
Oh, yeah, sure,
cheap
sure.
available,
Yeah, yeah.
So that
Yeah.
becomes part of the issue.
Yeah, sure.
But the other question that I had in mind is, did you take into account the cost of transport of the data from one center to the other? Because you've got fiber optics costs to deliver
Okay.
from one place to another.
Yes. Okay. Actually, 2 questions. First one is how to use the right cost for energy storage. For this one, as I just said, since the fluctuation of renewable generation is very fast, so the normal storage doesn't work. We need a very fast charge and discharge rate. You need to charge and discharge completely in 1 minute, which is not what we can usually do. And the second one is about the cost to move data from one location to the other. Right? The first thing is that our model is general enough to include that one. But for particular this problem is that the current system is the proxy. Okay, when we click the Google search, it will first go to the front end server of Google. And that server will decide which data center to send. No matter where he send, the incoming bandwidth is the same. Of course, there is another bandwidth, it's kind of peak bandwidth cost charging, like the peak demand charging. If we take that into consideration and to add another term into the cost our objective function, we can actually also optimize for that one. But that's a straightforward extension of this one. And we expect if we have another factor in, the saving will be more significant.
All right, it's great that there's so many questions, but since we're coming to the end of the time, I'm going to draw this to a close. If you're faculty and you still have questions, please come to the faculty lunch with Zinhua now down in the PCC conference room. If you're in the broader audience and still have questions, please come to the coffee hour tomorrow, 9 a.m. to 10 a.m. in the ECEE conference room. So thank you for coming, and let's thank Zinhua.
Thank you.